Okay, in this video, Logan is going to be demonstrating what structs are, as well as how we can go about using them. Logan.
All right, to begin with, let's make a new project so that we can try some of these things out. I'm going to make a new console application. Now, before we get started, let's have a quick discussion on what exactly a struct is. And I guess in the simplest terms, a struct is like a class that cannot be inherited from.
Okay, well, what is a class? A class was a means of going in and defining a new data type, a data type that can have behavior as well. Well, a struct is also a means of going in and defining a new data type, also with behavior, or the possibility of behavior. The big difference is, one, as Logan just said, inheritance. You lose inheritance with a struct. A struct is lightweight, where a class is not really lightweight. When a class is defined or instantiated, it's created on the heap, and there's some overhead involved, etc., etc. But with a struct, the struct is an actual value type, which means it resides on the stack, and it's going to be nice and fast. So if you've got a data type that you need to create, let's say you were creating your own vector or your own point, for instance, and we didn't have access to XNA. Let's say we weren't using XNA. Well, then, with that being the case, you might want to just create a struct, because there's no reason to set up a class because you're actually wanting this data to be represented. Well, it's just values. And if you're dealing with a value type piece of information, then create a struct if it's obviously a more complex data type than just a single int or float, etc. And that is exactly what struct is going to give us. Now, there are a few rules when working with structs, but we'll cover those as we start working our way through structs. So I guess, Logan, with that, let's go ahead and kick off this whole lesson by showing them the syntax. What does a struct look like?
Well, struct syntax looks very similar to a class definition, except we use the keyword struct. So we could say struct, and then we give the name of the struct. In our case, that's going to be point. And then we can follow that with an opening and closing parenthesis.
So all of our members are inside of the opening and closing parentheses.
Or rather, curly brackets.
Curly braces, yeah. And I just took that and ran with it. Isn't that great? But just like a class, here we are with opening and closing curly braces. Inside of these braces, that's where all of our members reside. And we have all sorts of members. I mean, we've got our fields, we've got our properties, we've got our methods. And we have constructors as well. So with that, let's go ahead and set up some fields.
Right, let's begin simple. Let's give this new point struct two fields. Let's give it an integer for x and y. Now I'm going to make both of these fields public for the time being, just so I don't have to get into properties and accessors for the moment. So let's make a public int x and a public
there we go.
int y. And really it's as simple as that. We have now defined a point struct which contains the members x and y, which are public integers.
So where integer is a data type, floats are data types, now we have a point, which is a custom data type, and a point contains two integers in this particular case.
So now let's take a look at how we would go about using this new data type in actual code. So what I'm going to do is jump down into the main method of the program class, and let's define a point variable. And I'll do this by simply saying point p.
Simple enough.
Really easy, isn't it?
No difference in saying int x.
And we can show that this is working. If we build the solution now, we see that while we have some warnings about things being uninitialized, the code does in fact build. And I could even run it. If I throw in a console read line just to hold up execution, then we could run this and actually see a blank screen but verify that the code runs. So we could put in a console read line and run. We do in fact have a working program. So now let's turn around and take a look at using those field members in the point struct.
Yeah, because obviously if you did something like int x, you could turn around and say x equals 5. But in this particular case, it's more like working with an object or an instance of a class when dealing with p for getting its internal members assigned.
Right, we have to access the individual members just as we would through a class. That would mean if we wanted to gain access to this point's x component, we'd have to just say p dot x. So there, and just looking at these, here's all the members that we have access to.
Ooh, but check this out. We see our x and our y, but we also have things like equals, get hash code, get type, and toString. Just a reminder from earlier discussions in the XNA class, basically everything comes from object. and toString, getType, etc. all reside within objects. So if we create a struct or if we were to create a class, we inherit that, period. Now, even though we're inheriting toString, getType, etc. here, that does not mean that we can further extend our struct point, because once again, as Logan said, inheritance does not exist when dealing with structs because we're dealing with value types, not reference types.
Right, basically once we get to the point, since value type itself actually extends from object before we get to struct, it's at value type where the rules kind of change and things are treated as value type and exist only on the stack. So because of that, struct is kind of like the dead end for inheritance at that point.
But it's pretty cool here, though. I was going to say that with things like toString, even though we don't have inheritance per se that we can use with structs, we can still override toString.
Right. Well, you could say that struct does inherit from something else.
That's right.
It's just that you cannot inherit from a struct.
That's right. So it's extending something else, if you will, by adding in our own members.
Exactly. But let's take a look at the two members we added here, x and y, and let's initialize them. Let's take p.x and set that to a value of 5, and then also set p.y to, again, a value of 5.
Okay.
So we can build, show that that's working. Before I run, let me turn around and display those values back out, read them back out to the console. So I'll throw in a console, write line this time. Now I'll write out x and y. Since I don't have any convenient point formatting code in place, I'll just simply concatenate the two values together. So that means we'll say first address the points x, and then concatenate, add on to that a comma, just to separate them visually, and then add on the final points y component. So now if we build and run, we see 5, 5.
Very nice.
So that shows that that is indeed working. We could maybe change one of these, maybe have y be equal to 10, and show that they are in fact two separate components.
Okay.
And so that's very simple usage of the data held within the point.
Now you could really go about demonstrating the differences between value types and reference types here if you wanted to. Just as a quick example, if you were to create a second point and then take that second point and say assign it to the first point.
Right, to see what's actually happening. Because really what's going to happen is when you assign one point to another point, the data gets copied.
Exactly.
It gets passed in the same way that any other value type would get copied.
And we just want to point that out because for those of you out there that have not worked with structs in the past and you're very comfortable working with classes now, you know if you were to take one class and assign it to, or one object and assign it to another, basically what you've done is both of those objects are pointing, they have the same reference.
Right, you could make two references to the same object so that if that object changes, both of those references will see the change.
And in this particular case, if Logan wants to go ahead and set up a second point real quick.
Sure, as a matter of fact, before I do that, let me refactor this current one. Let me hit F2, change P to be P1, so we have point 1.
Okay.
Then I could turn around and make a point for P2, and then initialize that as well. So let's say we have point 1 is 5 and 10. Point 2 would be some other values, or even point 2.
Just have point 2 equals point 1.
Point 1.
Yeah, that's what I was thinking.
Though, that if these were reference types, we would now have P1 and P2 referencing the same thing, but we're not dealing with reference types. We're dealing with a struct.
So now we can just copy and paste that console right line, and there we go.
Put in 2 and 2. Now on the first run, it'll all make sense because if these were in fact reference types, we haven't changed anything yet. So they should look exactly the same.
So we should have 5, 10 and 5, 10. And we do. Now, of course, at this point, it may look very much like we're dealing with a regular object that was instantiated from a class. But what if we were to turn around now after the P2 equals P1 line and add something like, all right, let's take P1 and set its x to a whole nother value.
Right, so if we turn around and said P1.x equals 100. Now, if these were referencing the same object, that would mean that both of these lines, so on the first component of each of these lines, should now be 100.
That's right.
If the values are copied, however, instead, if in this case the values were simply copied and there was no link to this guy's original values, then they will still be different. That means point 1 should be 100 and point 2 would still retain its original value, which was probably 5.
Mm-hmm.
So what is the result? The result is 105. So they are not linked in any way. They represent two distinct sets of values on the stack. There is no single object existing anywhere on a heap.
Exactly. So once again, as Logan said, when he did the line P2 equals P1, all of the information from P1 was copied to P2.
Now we could do something very interesting. We could show, once again, some of the similarities between struct and class. Though I'll have to do one quick thing before I get into that. I'll need to explain the constructor. Once I explain the constructor, we can show some of the similarities. And we can actually make the scenario where we have an object on the heap. But let me spend just a minute showing the constructor.
Okay.
Because, of course, I would need that if I were to treat these like classes. So, talking about constructors in a point, up to this point we haven't done anything with constructors or methods. We have simply declared the variable and then turned around and used the members. Now, first thing to look at is, one, what would happen if we had at any point failed to initialize any of the members? Just to get an idea of why would we even need a constructor for a struct.
And the funny thing is, up to this point, they're very used to everything just being initialized for them, if you think about it.
Right, and any other value type, data type, like integers and...
Yeah, you create an int, boom, it's 0. You know, you create a class that gets instantiated, everything gets set to 0 or to its default.
In the field sense. But here, since these are a value type only, this is a local variable, what if I were to comment out the line where we assigned the first point's y component?
And you may be thinking that, well, of course, y is going to be set to 0.
Because, I mean, up here, y is a field, so you'd think, okay, well, it should just be 0.
That's right.
If we try to build, we immediately get a compiler warning here.
Oh-ho.
So it's complaining about the entire thing at this point when we try to reassign. Well, that's kind of confusing, so let's comment out the whole line and try to build again. Now we get another interesting error. Now we have something that makes more sense. Once we get down to the first right line, the compiler is okay with the point's x field. Well, x has been initialized. It's set. Y has not been set anywhere. We have simply declared the variable and done nothing with it. It is an unassigned local variable. At least the field itself is. So unassigned field, and that's the error given here. Then, of course, we have other problems out from that with the second point. So now this presents an interesting problem. I mean, it's very simple with the point class to assign the two fields. There's only 2 of them. What if you had made a very complicated class that had many fields?
Or a very complicated struct.
Oh, excuse me,
they're so closely related. But yeah, if you had a very complex struct that had 15 different field members in them, do you really want to go through and hand assign 15 different ones, especially if you want them all to be initialized to 0 to begin with? Do you really want to go through there and explicitly do that?
Right, so go through 15 lines of code, 15 assignments, just to make your struct generally usable. Well, the answer to that would be no, and the good thing here is that a struct has a default constructor provided by the compiler. As a matter of fact, it's a constructor that you can't override or can't replace. But what the purpose of this constructor is simply to initialize all of their fields to their default values, which would be very convenient if you had many of them, or in our case, if we simply didn't feel like initializing y. The way we could utilize that is the same way we would call the constructor for a class. And that is to declare, we could turn around and do it in 1 line or do it in 2 lines, it doesn't matter, same as with a class. But let's say we wanted to do it in 1 line, we could say that point p1 is equal to new point. So we're calling new point as though it was a class, but really it's not that we're calling a class or a struct, we're calling a constructor.
That's right.
And structs have a constructor. This is the default constructor with no parameters. So let's see what happens when we try to build. So again, we're still not assigning y at all, so let's see what happens to this line. If we build, this error now goes away. It doesn't worry about the fact that we haven't done anything to y because we called the default constructor. That should set up y for us. And let me temporarily comment out the second line just to show that. If we run now, we have a y value of 0, which would be the default value of an integer that wasn't otherwise messed with. So that can be very useful. Again, here we only have 2, but if, like you were saying, we had 15 different fields that needed to be initialized, there we have one simple assignment. We don't have to worry about everything.
But this is interesting, too. Watch this. Go ahead and remove that equals new point out. All right. Now, some of you might be thinking, well, you could just go ahead and declare it, or initialize it up in the struct itself, so where you have public int x and say public int x equals 0. You cannot use initializers here.
There we get into some of the special rules for using a struct. There are no field initializers. If we try to set x equal to 0 and y equal to 0 by default, so we try to skirt the issue of having to initialize things, if we try to build, we get a very simple message saying that
you cannot have instance field initializers in structs.
Exactly. So that is
a no-no. So you cannot do that. I just thought that'd be a good place to point that out.
Right, just to show that the best bet to getting everything initialized to defaults would be to call the default constructor.
Mm-hmm.
And, of course, interesting to note that even if you call the default constructor, even though that's the same syntax that one would use to make a new class, a new instance of a class and throw it on the heap, this still has nothing to do with the heap. This is still simply assigning the values.
That's right.
The default constructor doesn't really make a new one of anything. It calls the constructor assigns the values, and the values are simply values stored on the stack thanks to this local variable.
Okay.
Let's see. So with this out of the way, I'm trying to remember briefly why I needed this set up. I think I was going to...
You're talking about further demonstrating something with...
With reference and value types,
That's
classes
right.
versus struct. So now that we know that we have a default constructor that can be called, let's see what would happen if we tried to use this point struct as though it were a class, actually going all the way back to the example where we were assigning one point to another. So let me initialize both points by using new point. So we call the default constructor to make sure we have all fields initialized. And let me put all of these lines back in. So again, restoring the full example, really this is now exactly the way it was before, except we have the addition of a call to the default constructor. So if I build, it should go back to exactly the way it was working, since while this is nice that we have things here, we've also changed them ourselves. So back to the original. The point of this example was, of course, to show that while we're assigning point 1 to point 2, we're not assigning a reference, we're copying the values from point 1 to point 2. That way if we change the point 1 values, nothing happens to the point 2 values. That means we changed the point 1 values getting 100, we did not affect the point 2 values of 5.
Right.
Now what if this had been a reference type? Well, let me simply change out the declaration here from struct to class, rebuild. Everything builds just fine since we do in fact have a call to the constructor, this time making a new instance on the heap. So let's see how this would affect it. If we assign point 2 to be point 1 and then change point 1's, are we in fact looking at a single object on the heap? If we run, we see that we've overwritten, or we're looking at the same thing. Changing point 1 to 100 caused down here point 2's x to be like point 1.
That's right, because both point 1 and point 2, remember, P1 and P2 simply contain a reference to the actual object that's sitting over on the heap. So both these guys are pointing to the same object. So changing the first one, well, you're still just simply changing the actual object on the heap that both P1 and P2 point to. So it doesn't matter who we print from because they're both going to print out the exact same thing because they're both referencing the same object.
Right. So again, that's kind of neat to show that you can go back and forth between class and struct and show the differences between value and reference. So what had actually happened in this case with point being a class, we had actually made a new throwaway point 2 before we reassigned it here. Mm-hmm. Whereas if this had been a struct, then this is being used for initialization purposes, and this line is simply doing a value copy instead of a reference reassign.
Right. Okay, so at that point, that gets just some very basic member fields out of the field members out of the way. So now I want to move into perhaps some methods.
Sure. As a matter of fact, let's first take a look at properties.
Okay,
and move into some interesting methods, just to show some of the other members that could be put in struct.
Absolutely.
Let's say that since the goal is, like you had said, we want to move into members, we want to add some interesting functionality to the point, some useful utility functionality. I first want to take these data, the data for X and Y, and make that private, and then turn around and have accessor properties to that data. So I could change these to private to begin with, and let me also change them to lowercase x and y. And then I'll turn around and give accessor properties to those. As a matter of fact, I'm going to make a region around these just so once I get done I can collapse everything down. So this will be a region called properties. And then we can end the region. And I probably need to drop this back. And there we go. So first we can make a property for x. So we could make a public property of type integer called x. And then to that we'll give a get accessor. The get accessor will return the value x. And notice that one can use the this keyword inside of a struct. Since this is technically an instance, I mean we can have as many of these as we want. These are instance members. And also we're going to put in a set accessor where we can say that this.x is equal to the given value. Then we can take the entire property, copy the whole property, paste it a second time, and change everything to y. So we have a public property called y, accessing this.y and setting this.y. So now all of this should work the same since these are now referencing a property instead. If I rebuild, I could probably jump back in and see that the icon has changed to represent X and Y as a property instead of as a simple field. But otherwise, the code should work exactly the same. And the same output as the Struct version before.
Okay.
So I can collapse down our properties region. And now let's do something a little bit more interesting. Let's add a utility method for calculating distance, much like we had done back in the Canon project. If you remember, to the WinForms-based Canon, we had to write our own distance utility method because there was no easy-to-use distance method in any library close to us. Now, in that case, we had made a method that simply resided in the main body of the code, the main class for the form. Now, with the point class, it would be convenient if the utility functionality that was to operate on point data was actually held inside of the point struct itself, so that we don't have a lot of cluttered code that seems disjointed. So what we could do is we could define a distance method inside of the point struct. As a matter of fact, I'm going to define this as a static method to begin with, since again, being used as a utility method, we don't have to have it work in an instance fashion. Instead, we just want a method available. We'll make that available from point. So what I'll do is I'll make a public static method that returns a double. The reason I'm going to return a double is simply because the math routine that we'll use is set to return a double. That way we don't have to cast. So this will be a public static double called distance. And distance is going to need to take in 2 points. We'll take in a point for point A and a point for point B. Now for distance, we're going to do the same things we had done back in Canon, and that is implement the Pythagorean theorem to find sides A and B of a triangle, square them, then get the square root to find C, which is the distance between the points. So I'm going to write this out a little bit more simplistically than it absolutely has to be written, but this should make it a little bit more clear when it's fully written out. So what I'll do is I'll first define 2 integers as sides A and B of this mock triangle. So I'll make an int for A, and I'll turn around and initialize that as well. We'll say that int A, basically what that means is side A of this triangle, would be the distance between X and Y of the 2 points. Or we could say point A's X value minus point B's X value. And of course I'm using the X field itself directly, but I mean we're inside a point, so we have access to the private members. So I could turn around and do the same thing. Int B, or side B, is the distance between the point A and B's Y. So the point, point B dot Y minus, point A dot Y. It really doesn't matter which way we go because we're going to be squaring all of these anyway. So point B dot Y. So so point A minus point A minus point B for X and for Y, giving sides A and B. Now we can define a double for side C, and that's going to be equal to side A squared plus side B squared, and then getting the square root of that. Basically, side A squared plus side B squared would equal side C squared. We want C by itself, so we'll get the square root.
Right.
So that is...
Just go ahead and throw your equals in there.
Right. Side C equals math dot square root. Now we're getting the square root. We need A squared, which will be, I'm going to throw down the parentheses first. A times A. I'm sure we could probably find a power function somewhere, but I'll write this as simply as I can. A times A would be A squared. B times B would be B squared. I guess I don't technically need these. We can just rely on order of precedence to take care of this for us. So A squared plus B squared, getting the square root of that, storing it in a side C. Then finally we can simply return the value in C as our distance. So again, just a quick revisiting of the distance method. But let's try this out now. Let's jump down and do a console write line for the point's distance. So after we've done everything, we've done these 2 calculations here. Let's throw a console write line. I'll write a blank line out just to space everything down. So console write line again. This time, let's write out the distance between points 1 and 2. So we could say point dot distance of point 1 and point 2. So if we run
missing a closing. parentheses.
And missing closing parentheses. We'll close it off if we run. Now we get some number. Though I want to prove that this is working, let's come up with a more simplistic calculation. Like let's take 0.1 and set that to a value of 0 and 0. And 0.2, I'm going to erase the assignment test that we were doing and make 0.2 equal to maybe 1 in x, 0 in y. So if we had drawn this out on graph paper, we should be exactly 1 unit away. 0.2 is 1 unit away from 0.1. So distance in this case should return a value of 1.
And it does.
So now I could set 0.2 to a value of 1 and 1, and we should get something like 1.4, going the diagonal across an imaginary 1 by 1 square. And I get 1.4 and
some change. Okay.
But that is in fact working. So that's showing a method, in this case a static method, being created from a point struct. Now what if we wanted an instance method? What I could do is I could define another overload of distance, this time that works from an instance of a point. So what I could do is I could make a public double called distance. This time the idea being that you take any point that exists and ask it what its distance is from some other point. So we'll feed in a point here. I'll just call this one point P. So we ask this point what its distance is to point P. And we can do that by actually using the existing static method. So we could simply return the distance between this, ourselves, and the given point P.
Very nice.
So now we could rewrite our check here, where we could say what is the distance from point 1. So let's ask point 1, what is your distance to point 2? And if we run, we get the same value. So this is the same calculation, but this time being called from an instance stance. And
Very cool.
Let's see. I think with that, there's only one more thing I want to cover. We've got fields, properties, and methods. Let's show doing a simple override. And what I mean by that is, let's say we wanted to make it easier to write out the value of a point. Because right now, if we want to dump a point out to the screen, we have to do some string concatenation for every single time that we want to look at a point. Because what would happen if we just did a write line for a point? Let me temporarily comment out all this code just in case I want to get back to it in a minute. And instead replace it with a console, spelled correctly. Let's do a write line for P1. What happens when we write out a point to the console? Well, we get the default implementation of toString, which is just going to give what it is back. This is console application.point, so what it is. What would be more useful to us is if this mimicked the behavior of the vector in XNA, the vector2 or any of the other vectors, where it gives a dump of the actual data held within the vector. And if we wanted to do that, we could change the functionality of toString, because really if we'd called upon toString, we would get the same result. And that's really what's actually happening behind the scenes. So we know we need to change the behavior of toString, and we can do that by overriding it. I'm going to jump back into our point struct and make a public override for the toString method. And instead of returning base.toString, let me return a string similar to what we had been concatenating in our own write lines. Let me just copy x plus a comma plus y. Except in this case we don't have to worry about P1. We can just use a local this.x and this.y. So if we build, everything's working. So let's see what the result of doing write line for a point is now. 0, 0. And in this case, okay, yeah. For a second I was wondering why it was 0.
So if you just change it to P2 real quick, well, that'll work too.
So 5 and 2, we see 5 and 2. And that means we could clean up some of our code. If we bring our main code block back into place, we could take all of these and just say write line P1, write line P2, take out our test line, and there we have substantially cleaned up the code, but getting the same result.
Very cool.
And with that, I think that's all of the things I wanted to demonstrate about using structs.
Okay, just as a reminder, they of course can use constructors. They cannot have a parameter-less constructor.
Oh, that's a good point. Let me interrupt you for just a second. There
Sure.
was one last thing that I wanted to show. We had touched on briefly that you can put constructors into the struct, but we had only talked about the default one. Let me show an example of creating your own constructor. Now, you cannot replace the default constructor. You can't do something like public point no parameters and expect this to work. You cannot contain an explicit parameterless constructor. It already has one and you're not allowed to change it.
That's right.
Now you could go in and make a constructor with parameters. For example, if you remember to the way the color struct works in XNA, where you can say a new color, and you are given the option of feeding it red, green, and blue bytes. So if you want to start off with a color and immediately have values and not have to do separate assignments afterwards, what if we wanted our point to function with that? What if we wanted to be able to say new point, give it 2 values, and just automatically have a point that's set up? We could do that here if we made a public constructor and took in some parameters. I'm going to take in an int x and an int y. Now with those, if I try to build once again without doing anything in the constructor, you'll see we get 2 more errors. And that is, if we happen to define our own constructor, we absolutely have to assign all of the fields. Since the whole idea of calling the constructor is that your entire struct is now usable in all regards. So the compiler makes sure that we initialize everything. Even if we had fields that didn't have to do with x and y, we would still have to initialize them to some value. But in our case, x and y will take care of everything. So we could do an assignment where we store x and y in this.x. So this.x equals the given x. This.y equals the given y value. Now if we build, everything works. And we could replace these lines. If we wanted point 1 to contain the values 5 and 2, we can now say point. And if I bring up the list of possible parameters, you can see that we have 2 overloads here. We have point by itself, again the default constructor, or we have a version of point that now takes in x and y. So we could feed it 5 and 2. Now we have 5 and 2. Or of course, if we change this to anything else, just to prove that other numbers are in fact working, anything we want. And so I think with that, let's see.
So that basically walks through different members, fields, properties, methods. We also touched on constructors. We demonstrated the difference between the value and reference types and really drove home the idea that structs are value types. These structs cannot be further extended. Inheritance does not play, though of course we can override things that we inherited from objects, such as toString. I think that's pretty much everything. Just the key thing to remember, if you need a very quick data type that is custom and you don't need all of the functionality of a class, this is the way to go. Okay? Anything else you want to add, Logan?
I think that pretty much sums it up. Again, like you had said, just a lightweight data type. So if you need a collection of data and some utility functionality to go along with that data, a struct will work just fine there.
Okay, and with that, that is going to wrap up this video. Thanks a lot.